Hello there, my name is Jeroen and today's talk is on AI, trust and blockchain. More completely, how could we build trustworthy AI systems by using blockchain for higher data integrity. And this presentation is then about data and how users can trust the data that is used in AI systems. We will cover a few topics, a short introduction into artificial intelligence, and then one of the main problems that is connected to artificial intelligence and trust, and how blockchain could help there to increase the trust. And we're going to end this short presentation with a few concluding remarks. So let's first start with artificial intelligence. There are many definitions on what the field is, in this picture you see a few of the application areas that are connected to AI, like learning, reasoning, problem solving. But in general, you could say that there are two main approaches within the field of artificial intelligence. There's a symbolic approach where you have explicit knowledge representation, you have language models, you have problem solving and reasoning. And you have a connectionist approach where intelligence is achieved by learning from data. So fields like machine learning, neural networks, you might have heard of them, they are in this second approach. At the moment, so in this decade, the connectionist approach is the most successful approach in the field of AI. So a lot of things are happening there. But we're going to start by giving you an example of the first approach, so the symbolic approach. Here you see the Google knowledge graph in this screenshot. And the idea of a knowledge graph is that you are somewhere in a knowledge space and you have all kinds of contextual data that are related to the place where you are in this data space. In this case, there's a search term, Larry Page, and you see all kinds of connected links to this search term. So the knowledge graph is a graph of connected data, collected linked data, so that you can get from this spot, this Larry's Page spot, to things like his Wikipedia page. You can see what prizes he has won, where he studied. And this is a very helpful thing, Google thinks, because it can help you explore the space, the information space. Of course, this knowledge graph is also very important for companies because they like to optimize their presence in this knowledge graph so that they can be better found. When you're a company, that could be important. But the idea here is that knowledge is explicitly represented, and it's found, of course, but there's a hard link in the data. Machine learning, on the other hand, tries to learn from data. So there's not an explicit knowledge model behind it, but it tries to learn from a training set that contains exemplary data. And by training the system, you learn the system about the data that's in the training set. And you can do something with this trained system. To give you an example, here you have a large collection of onions. Harmless example. And you could imagine that the larger picture in this on this slide is your training set. So you feed the system with all kinds of examples of onions. And you see pictures of one onion or a lot of onions in different colors with different backgrounds. But every example given enhances the understanding of the system of onions. What you need to do is that you make a connection between the picture given and the label that is connected to this picture. So, and what happens when you have trained the system, then when you present a new picture, which is not part of the training set, like the small picture on this slide, then you can ask the system with what amount of surety, how sure are you that this new picture that I'm giving you is an onion? And the system can tell you something like, okay, I think with 0.94 this is an onion, because it matches with the other onions that I've seen in my training set. And it would probably tell you also something like it's 0.15 a car, because it doesn't match really with a car. Maybe some of the curves you can also recognize in the car, but it's not a car. It's probably an onion, and it's probably not a car. There's of course an internal representation, but it goes too far for this presentation to give you an overview on how that is done. Well, this way of training a system, creating an AI, some say, can be applied in different situations. So I gave you the example of a classification system, where the trained dataset is used to guess if a new photograph, in this case, is given, then the system can classify it. It can say, okay, it's a car, it's not an onion. But these systems are also used in, for instance, in self-driving systems. Here you see an example of a self-driving car, and this car uses cameras, and it uses the cameras to get an understanding of what is around the car. And understanding the situation of the car requires that the car is capable of recognizing what is another car, and what is a cyclist, and what is a pedestrian. So this system is trained in recognizing, in the same way as with the onion example, to understand the surroundings of the car. There are many more examples of these AI systems, but I want to talk to you through one of the other examples, a text-to-image system, which gained a lot of attention lately, Stable Diffusion. It's a kind of reverse classification. The onion example that I gave you is based around the idea that I present the system a new picture, and then the system, as a result of the classification process, gives you a text. So it's a kind of image to text classification. But in this Stable Diffusion example, it goes the other way around. It goes from text to images. So you have a trained system with pictures and all. And then based on that system, on that model, the user gives the system a prompt, a text, and then the system creates out of it a picture. And a picture that isn't part of the training set, but it is created on the input that the user gives the system. Then you get these kinds of things. Here the input of the system was, okay, give me a giant onion in a field of strawberries, which is perfect and detailed. And then the system generates this picture. And indeed, we see strawberries, we see a giant onion, and we see a field. Funny things with this way of training a system is that not only the objects can be reproduced in a new picture, but also styles, colors, and spheres. That's very atmospheres. I mean, that's incorrect on this slide. So and it gives you a whole nice field to play with and be surprised on what the AI generates for you. Okay, now you have an idea on what the field of AI is more or less. Okay, let's now go into the topic of AI and trust. We had this example, the onion training set, where we present the system onions, images of onions, and we do so in order to enhance the concept of the AI system of onions. So in the table here you see 4 pictures. Now you see 4 links to pictures, where there is for every picture there is a label, which is important, so the system knows, okay, the picture that I'm viewing now is labeled an onion. So the model is extended with every picture in the training set that is added. And maybe the name could also be used to further enhancement of the understanding of the system of onions. But now there is a problem, and the problem is the following. The training set used, in this case for onions, could be a false training set. It could be skewed. Some onions could be more present in the training set than other onions. And if that's the case, then the AI system based on this training set will produce biased results. So if in my opinion onions are all purple, I would present the system purple onions. And so the end result, the result of the AI system using this train set will also be purple onions. You could say, okay, well, that's not a big deal. One of the big deals is that for the user, it's very hard at the moment to understand what data was used to train the model. And this brings us to one of the ethical challenges that we have in the world of AI, in the field of AI. So the purple onions example might be harmless. Maybe biologists would say, okay, you should not train your AI system with only purple onions because there are more varieties of onions. But it becomes more complicated when you build a training set that, for instance, connects race with criminal behavior. And you use that training set to discriminate groups of people in society. So understanding what data is used in the AI system to produce results is important for the user. Not knowing the training set and its possible skewness is a danger. And this danger could decrease the acceptance of AI systems, which is not our main problem, of course, but it could also do harm in society. So it would be better if we had AI systems that are explainable, that you can say, okay, I've come to this conclusion that I show you purple onions because only thing I know is that the world exists of purple onions. If that's the case, then the user can say, okay, this is a very limited model that is used to train the system. So acceptance of AI systems will be higher, but the danger in society of self-explainable or explainable AI system will also be lower if people understand why the system behaves in the way that it is. Now, how could blockchain improve the trust in these AI systems? Blockchain, as you all know, probably has a few important characteristics that can be used to increase the understanding and the acceptance of these systems. One of the main things of blockchain-based systems is that the data added to the system, an append-only system, is immutable. You cannot change it afterwards. So you cannot cheat with that to say, okay, but actually green onions are also part of my dataset. Another thing that's brilliantly done is that it's publicly accessible and easily checkable. So data published in a blockchain can be there for everyone, and it can be used to check the correctness of data in an easy way. Now imagine that you build a kind of proof system or an audit trail system where you can say, okay, I can show the user what data was used in this training set and that it wasn't changed. And I can see what has been done with this data in this AI system in a publicly easily checkable way. If that is done, then the understanding of the user in this AI system will be higher, and it will be more easy to understand if the AI system behaves in an awkward or skewed way. How can this be done with blockchain? Well, easily. Imagine that you have a training set that you use for your AI system, and that you create a hash out of this data set, training set, and you store this hash in a block on the blockchain. Then that stamp proves what data is used for your training set. So somebody doing an audit could go back and could see what the hash is stored in this blockchain. And it could compare it with the training set that is told to be used for this AI system and compare them. And if these hashes are equal, then that's the truth. And the same can be done with the resulting model that is used for the AI system. Also, the hash of that model could be stored on the blockchain to see if there's no, to show what model is exactly used to produce the data, to produce the outputs of the AI system. This can all be done in a very easy way, and you see the big companies, the big IT companies, going along these lines and coming up with the first architectures to do so. But it doesn't require much, it doesn't require specific efforts to create it. You could use off-the-shelf features of blockchain-based systems in order to provide this audit trail for AI systems. So we come to the end of this presentation. I think what we try to argue is that the blockchain could be used to prove what data was used for a training set. And we can use blockchain and its immutability characteristic to prevent tampering with that. So you can prove, okay, this is the exact data that was used. And that by doing so, we provide auditors an audit trail on these training sets, on these data sets. Well, that was it. I hope you enjoyed it. Maybe see you next time.